In this video, we will be looking at how to find the absolute maximum and minimum values of a function when you're given a specific interval. So we're going to start off with a very visual example. I have three polynomials here, and we're going to identify the absolute max and mins within this specific interval. So for our first example, we have this parabolic shape. Normally a parabola would go, in this case, down forever. However, we do have it cut off. So looking at this right here, that is as low as the parabola will get. So we have a minimum of -12. And right here at the vertex is our maximum of 6. So you'll notice the minimum is one of the endpoints on this parabola and the maximum is the vertex. And at this vertex, we know that if we were to draw our tangent line, it would be horizontal. For our next example, my minimum value is, again, one of the endpoints. So this looks like maybe a cubic function. I'm going to estimate this as a minimum of negative maybe 29.5 because it's not really reaching -30. And then our maximum is this point here, where again, at this point, the tangent line would be horizontal. So we have a max of 2. And finally, for our last polynomial function, I have a maximum right here. It's a maximum of 76, let's say. And our minimum is down here. This time the minimum is one of those points where the direction changes, a turning point, if you will. Tangent line's horizontal there. We have a minimum of, I'll just say -8.1 because it's not quite at -8. So you'll see sometimes your max or your min will be at a point where the direction changes. And sometimes your max and min will be at the end point for a specified interval. So when we're trying to find the max or min values of a function for a specific interval, let's say x is between a and b, we have to calculate f at x at two different places. First, at our critical points. Our critical points are where our derivative is equal to 0. So that's where our tangent lines are horizontal. So for example, here, 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 those are all critical points. But we also need to test f at x at the endpoints. So in this case, if we're looking at x between a and b, I would have to evaluate f at a and f at b. And then I would just compare which of those values is the biggest for the absolute maximum, which one's the lowest for the absolute minimum. So once again, we're testing the endpoints and we're testing those critical points because those critical points are where we're changing from an increase to a decrease or a decrease to an increase. So that is a potential max or min. So let's take a look at our first example. Determine the extreme values of the function f at x equals -2x cubed plus 9x squared plus 60x plus 4 on the interval x is an element of all real numbers between -6 and 6. All right, so first thing, I'm going to find my derivative because I want to find those critical points. So we're going to have -6x squared plus 18x plus 60. I'm going to set my derivative equal to 0 here. And there is a common factor, so I'm just going to factor out a -6. And that'll give me x squared minus 3x minus 10. And then I can get a nice factorable expression, trinomial here. So we'll have x minus 5 and x plus 2 when we factor. So our critical points are when x is equal to 5 and x is equal to -2. So first thing I want to check for are these critical values within the interval. Yes, there are, so I'm not going to cross any of them out. And now I'm going to do my tests. So I'm going to test the critical points. I'll just write CP. So I'm going to evaluate f at 5. So that would mean I'm doing -2 times 5 cubed plus 9 times 5 squared plus 60 times 5 plus 4. And if I punch that into my calculator, I get 279. Then if I try f at -2, and again, same thing, replace x with -2, I end up getting -64. So right now that could look like a maximum and a minimum there, but we never know. Maybe the endpoints are actually a little higher or a little lower than what we have for our critical points. So I'm going to test the endpoints as well. So my endpoints are -6 and 6. So I'm going to evaluate f at -6, punch that into my calculator, and I get 400. So that's bigger than the 279 from f at 5. And then I'll try f at 6 as well. And if I punch that in, I get 256. So when I'm looking at this, this is a max, this is a min. So let's do a little visual just for the justification in case we don't believe what's going on. So there's -6. There's +6. So at +6, we're, let's say, 256. And at +5, we're at 279, so a little higher. So something like that. This is what it's going to look like. And then at -2, I'm at -64. I don't know. Obviously, this is very rough. And at -6, I'm at 400. I'm just going to go way above. So this is kind of what we have. And if we use our knowledge of polynomials, this is a cubic function, so I did expect opposite end behaviors. But also with this negative leading coefficient, I know it would have gone from quadrant 2 into quadrant 4. So in reality, if it weren't for this interval, this cubic function would look something like this, arrows at the end. So there would be no absolute max and mins because one arm is going to positive infinity, the other goes to negative infinity. But because of this interval, we now have a maximum here, okay, and then a minimum here. And you'll see at the critical points, that's where the direction would change. So those would be local max and mins. So this one here, although it's not the absolute maximum, it would be a local maximum within this area. And then this would go down forever, but that restriction stops it at x equals 6. And there we are. So visually, we can see where we have that change in direction, where those tangent lines are horizontal. That's potential for max and mins because there won't be anything directly below that within this area because that's where the direction changes. Likewise here, there won't be anything bigger than whatever this value is because that's where the direction changes. But I could also have those max and mins beyond those critical points at the end points. So we have to test everything. So now let's try another example. And here we have a rational example. So first I would take a little peek at my numerator, see if I could factor anything here, x squared plus 2x plus 16. For 16, we could do 2 times 8, 4 times 4. No, nothing's gonna help us factor it. So I need to find these extreme values. So I want to find my critical points of this function, and I will also test those endpoints. So I'm going to start with my derivative. And my derivative will require a quotient rule. So the derivative of the numerator is 2x plus 2 times the denominator minus numerator times derivative of the denominator, and the derivative of the denominator is 1, so that's great, not even going to write that, all over the denominator squared. Just going to do a little cleanup here. So I have 2x squared plus 4x plus 2x, so 6x plus 4 minus x squared minus 2x minus 16 all over the denominator squared. And then x squared plus 4x minus 12 over x plus 2 squared. And in terms of a little restriction, I know I won't be able to take the derivative at -2. I would have also known from the beginning because there's a vertical asymptote there. And now I'm going to set my derivative equal to 0 to solve for those critical points. And then we can cross multiply or just multiply both sides by that denominator, and we get 0 equals x squared plus 4x minus 12, and then I'm going to factor. So we get x plus 6 and x minus 2, which makes my critical points at -6 and at +2. Now the critical point at -6 is out of my domain for x, so I'm just going to cross that out, and now I'm going to test my values. So I need to test my critical point, I need to test 0, and I need to test 14. So I'm just going to go into my original function g of x, not the derivative, and I'm going to replace all of the x's with 2 to begin with. Just punch it into my calculator, and I get 6. When I punch in 0 for all the x's, I get 8. And when I punch in 14, I get 15. So now I take a look. Here's my max, and here's my min. And I'll just write a little therefore statement. Therefore, the absolute max occurs at 14, 15, and the absolute min at 2, 6. All right, final example, a little word problem here. The surface area of a cylindrical container is to be 100 centimeters squared. Its volume is given by the function v at r equals 50r minus pi r cubed, where r is the radius of the cylinder in centimeters. Find the maximum volume of the cylinder if the radius cannot exceed 3 centimeters. Round your answer to the nearest hundredth. So, a few things here. I see the word max volume, so I know I'm going to need to find my critical points and test them. And I also see that the radius cannot exceed 3 centimeters. So that gives us our restriction. R is going to be between 0, but not including 0, because then I won't actually have this cylindrical container, and 3. So when I test my values, I'm going to test 3 and something really close to 0 to try to find that maximum. So we're also told something about the surface area being 100 centimeters squared. That doesn't affect our work here. That 100 centimeters would have been helpful if we weren't given an equation to model the volume, but we were. So we don't really need that 100 centimeters squared. So let's go ahead and find those critical points. So I'm going to take the derivative of my volume. So 50 minus 3 pi r squared. Remember, pi is a number. Don't treat it like a variable. So there's our derivative. I'm going to set my derivative equal to 0, and I'm going to solve. So I'm going to bring 3 pi r squared to the other side. I'm going to divide both sides by 3 pi, and then I'm going to square root both sides. And I know I would have positive or negative of it, but the negative radius isn't within the domain. So negative not in domain. So so I'm not even going to consider that. I am going to clean up my radius though, because I don't want that radical in the denominator, because remember, this is what we actually have. So when I'm cleaning up, I'm going to do a few things. I'm going to rationalize the denominator while also simplifying that numerator. The square root of 50 is the square root of 25 times 2, so 5 root 2. And then now I'll multiply top and bottom by the square root of 3 pi. So I'll have 5 square root of 6 pi over 3 pi. So there's our exact radius. And again, I ignored the negative because it wasn't within my domain. And now I'm going to test some values. So I am of course going to test my radius from the critical point. I'm going to test 3. And although I can't include 0, because then I won't have a volume at all, I'm going to test something really close to 0, just to make sure that that radius won't maximize the volume. So now I'm going to go to my calculator. I will estimate the volumes if I don't get an exact number. So when I plug in that critical point, I get around 76.78. When I plug in 3, I get approximately 65.18. And when I plug in 0.1, I get approximately 5.0. So looking at this, I know I want maximum. Here's my maximum. It was not the endpoints. So therefore, the max volume is approximately 76.78 centimeters, and it occurs at that exact radius. It didn't ask us for the radius though, so I'm not going to write it for my final answer, but there we are. So once again, this was a word problem. I saw the word maximum, so I knew I had to find the critical points to test, and I had to think about what my domain might be for this variable to test those values. Now, just a note in terms of testing for max and mins, we could also find max and mins not just by plugging them back into the original formula, but thinking about if the tangent lines to the left and to the right are positive or negative to see if we're on that increasing to decreasing pathway to get a max, or from decreasing to increase to get a min. But right now, since we do have these intervals, testing our critical points and endpoints is a good strategy. But we'll see that first derivative test is what we're going to call it later on.